So today I'm talking about numbers in JavaScript, or why 10 quadrillion is equal to 10 quadrillion and 1 in JavaScript. My name is Evan Fair. I tweet occasionally at Evan Fair. I've got way too many R's in my last name, so if you put too many R's in there, you know you've spelled it right. In the beginning, humans were bacteria, and we evolved into fish, which evolved to have hands, and each hand had 5 fingers, so a total of 10 fingers. And so we developed a base 10 number system, which means that we have 10 digits, 0 through 9, and it means that every power of 10, we need a new place value, or we need a new place for writing down the value, like this. I think it's time for a demo. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Note that the next number is a power of 10, so we need a new place value, or we will use an additional digit for writing it, and 10. Okay, let's keep going to 100. Oh, yeah, thank you. Practiced out in a long time. Let's keep going to 100. 11, 12, 13, 14, 15, 16. Of course, I'm just trolling you now, and 99. And the next one is a power of 10, so we're going to need a new place value, or a new digit for representing this number, and 100. So that's the end of the demo. You guys can clap again if you would like. In the beginning, computers were vacuum tubes. They evolved to be transistors, which evolved to have 2 fingers. Now, those of you that have worked with computers before are probably thinking to yourself, yeah, those are both middle fingers because I've had the computer give me the bird a few times. That, in fact, they are not the middle fingers. That is false. They are index fingers or the pointer finger, which is why neckbeards are always mumbling about pointers. So anyway, computers evolved to have 2 fingers, and they developed a base 2 number system, which means they have 2 digits, and means that every power of 2, they get a new place value, or they need to use an additional digit for writing down that number, representing that number, like this. I think it's time for another demo. 0. Now note, I'm using a 2 as a subscript here. Throughout this presentation, whenever I'm showing a number in base 2, I will put a small 2 subscript there so you know that it's base 2 and not base 10 or any other base. 1, the next number is a power of 2, which means we get a new place value, or we'll use an additional digit. 2, 3, and the next number is also a power of 2, so another place value, and 4, and we're done with the demo. There are a number of ways in which computers can represent numbers. We're going to talk about the 2 most common ways. First, let's talk about integers. So in order to represent an integer, we need to set aside some space in memory for to hold the binary digits, and we often refer to binary digits as bits. So for now, we're going to use 5 bits to represent an integer. Your computer likely uses 64 bits, but that doesn't fit very well on slides, and so we will use 5 bits. So here we have 5 bits representing the numbers 0, and 1, and 2, and 3. And this should look all familiar to you because we're just counting in base 2. Now, when using integers, there's some gotchas, some things you need to be aware of. So if we have 31 represented as a 5-bit integer, and you add 1 to it, you get 0. And that is called overflow, and it looks like this. If we have 0 represented with 5 bits, and you subtract 1, you get 31, and that is underflow, and it looks like this. So that's the end of the gotchas with integers. In fact, that's the end of all gotchas you'll ever run into with computers. So from here on out, everything is easy. So far, we've only talked about positive integers. And you may be wondering, what do we do with negative integers? Well, negative integers are represented by reserving a special bit called a signed bit. So here we have a signed bit, 0, which means it's a positive number. If the signed bit is 1, it's a negative number. And so it's time for another demo. Here we have the number 1. We know it's a positive 1 because the signed bit is 0. And also note now we switch from 5-bit integers to a 6-bit integer. That last signed bit is part of the representation there. So now we're going to switch the sign bit to 1, and so now we have a negative number, and of course it is negative 31. Now that was pretty simple. That's the end of the demo. And at this point, you may be feeling a little confused. You may be angry, and you may be questioning or not whether or not those two fingers are the middle finger. So you may be asking yourself, why did the number go from positive 1 to negative 31 when all we did is change the sign bit? Well, the reason why is computers use a format called 2's complement. And so let's talk about how we convert a positive number to its negative counterpart using 2's complement. There are 2 steps. The first step, swap all the 1s and 0s. If it's a 0, it becomes a 1. If it's a 1, it becomes a 0. And the second step is we add 1. So let's have another demo. This is the 4th demo. This is a pretty demo-heavy talk here. So we're going to go from positive 31 to negative 31 using the rules of 2's complement. Here we have positive 31. The sign bit is 0. We know it's a positive number. And the rest of the bits are 31. Now, the first step is to swap the 1s and the 0s. Note this automatically sets the sign bit to 1, so we now have a negative number. And the second step is we add 1, and this gives us negative 31, using the rules of 2's complement. Now, note this looked like what we thought negative 1 should look like, but using 2's complement, we know it is negative 31. So I still haven't answered why. Why not pick something simpler? Why not use the format that we all thought was intuitive? Well, the reason why is if you didn't use 2's complement, you would need to have 2 chunks of silicon, one for doing math with positive numbers and integers, and the other one for doing math with negative integers. With 2's complement, you can use the same chunk of silicon for both. It doesn't even have to worry about the sign bit. It just does the math as if it was positive, and you get the right answer. And that is frickin' awesome. Now, why 2's complement works like this is going to be left as a homework assignment. You guys can go home and write 1s and 0s on paper and do the math and see that it works out, and it's awesome. So how can you remember the name 2's complement? Well, the 2's part is easy because there are 2 steps from converting a positive integer to a negative integer. And, that's 2 steps. And the complement is easy to remember because as a computer scientist, when your significant other asks you for a complement, you, of course, are going to want to respond using negative numbers. So now you'll never forget the name 2's complement, and you're welcome there. So there's one more thing to say about integers. They are very good at representing whole numbers like 3. They are not good at representing numbers such as 3.7, and if you try, they just truncate it down to 3. And now you know everything there is to know about integers. So because integers aren't good at representing decimals, computers, or numbers that have a decimal point in them, computers have a second way of representing numbers called floating point. Floating point numbers look like this. And they note they have a decimal point, and it floats because it is less dense than water. So remember, integers were made up of a sign bit and a whole bunch of other bits. Hold on one second. I am now going to skip a version of Docker. Apparently that popped up right now. Great timing, Docker team. Remember, so integers have a sign bit plus a bunch of other bits. Well, floating point numbers, they are a bit more complicated. JavaScript uses 64 bits for floating point numbers. But those bits are divided up into 3 main components instead of just 2. So instead of the sign bit plus everything else, you have 3 main components to it. You have a sign bit, just like with integers, and that takes 1 bit. That's what we call the sign bit. You have the exponent part, which uses 11 bits. And when we're talking about exponent, keep in mind we're talking about this operation, the operation you get with MathPal. So you have the base, and you raise it to the exponent. So anyway, the exponent part takes 11 bits. And then we have the fraction part, which uses 52 of those bits. So 52 plus 11 plus 1, that's our 64 bits. And they are combined like this in this formula, which is -1 raised to the sign times 1 dot the fraction in base 2 times 2 to the exponent minus 1023. And now you understand floating point numbers. The end. Any questions? Okay, just kidding. Let's examine the components of this equation. And there are 3 main components to it. They are 3 components all multiplied together. We're going to talk about each one in turn so we understand how they work. First part, we'll start with the sign. So, -1 raised to the sign power. What does this mean? Well, if the sign bit is 0, you get a +1. If the sign bit is 1, you get a -1. And that positive 1 or negative 1 is multiplied by the rest of the equation, which means the answer will either be positive or negative. So in other words, the sign bit works exactly the same as it did with integers with floating point numbers. Okay, let's talk about the fraction part. So we have 1.fraction, and that is in base 2. And that's kind of messed up, because here I am telling you how does computers represent floating point numbers, and I'm giving you part of the formula, and it has a floating point number. Is there a way that we can represent this without using floating point numbers? Well, remember that the fraction part uses 52 bits. And if we pretend that there is a 53rd bit, this isn't actually stored, but we just pretend there's a 53rd bit, and that is always set to 1. And then we take the fractional part and we kind of lay it out there, and then we multiply all that by 2 to the negative 52. Is what that does is that takes the decimal point and effectively shifts it 52 spaces to the left, and you end up with this. So we can represent this without actually having to use floating point numbers to represent our floating point numbers. So we have the sign part. It's going to be either positive 1 or negative 1. The fraction part is going to be a number between 1 and 2. If the fractional bits, those 52 bits are 0, you're going to get 1.0. And if it's a really big number, you're going to get 1 really big number, which is really close to 2. So the last part is we have the exponent part, which is 2 raised to the exponent minus 1023. So you may be wondering, it's like, well, why do we have exponent? Why do we subtract 1023 from the exponent number, from those 11 bits? Now, remember back when we talked about 2's complement, and it was a little bit confusing? Well, in floating point, they decided not to use 2's complement. The exponent part, those 11 bits, will always be positive, and then in order to get negative numbers, because they need negative numbers here, they subtract 1023. So the exponent part, with 11 bits, you can get a number between 0 and 2047. When you subtract 1023, the range of that number becomes minus 1023 to positive 1024. Now, minus 1023 to positive 1024, some of us kind of think that kind of is a weird range. We'd prefer it to be symmetrical. We really want it to be minus 1023 to positive 1023. And so we want to get rid of that value when the results are going to be 1024. And the way you do that is when the exponent bits, those 11 bits, equal 2047, and then you subtract 1023, you get that 2024. And so one of the ways that we could fix this problem, this symmetry problem, is to say we're never going to allow the exponent bits, those 11 bits, to have a value of 2024. But maybe even better than that, instead of getting rid of it, we'll say, well, we're going to treat that as a special value. And it's kind of special because that value for those 11 bits means they're all 1, and that kind of looks special to us. So we're going to come back to later on about what we're going to do with that special value a little bit later. Just keep in mind that's a special one. So we've gotten rid of that special value. We now have the exponent of a range of minus 1023 to positive 1023. And so now we have the third part of the equation. We're taking 2, we're raising it to a power of some number between minus 1023 and positive 1023. So going back to our formula, we've got the sign portion of this equation, positive 1 or negative 1. Oops. We've got the fraction part, where it's going to be a number between between 1 and 2. And then we've got the exponent part, which is 2 raised to some power between that number range there. And there's a lot of detail there. Well, if we ignore the detail, if we squint at this a little bit, is what we really have is a number raised to an exponent. And this is great, because when you're dealing with exponents, you can get numbers which are really, really large. And, for example, if you take 10 to the 100, you get 1 followed by 100 zeros, and that's a really, really large number. However, with a negative exponent, which we can have because we subtract the 1023, you can also represent numbers which are really, really small. For example, 10 to the negative 100 gives us 0.100 zeros and then or 1 there, or somewhere around there, maybe 99 zeros. It's really, really small either way. And that is freaking awesome. So floating point numbers can represent numbers which are really, really big and really, really small. But the numbers that it can accurately represent are not evenly distributed across the number line. So let's understand this a little bit better. Let's take a step back and look at a graph of integers. Here are all the integers between 0 and 100 that can be accurately represented. I mentioned before, like you can't represent 3.7. These are the ones that can be accurately represented. Notice they're evenly distributed across the number line. There are just as many integers between 0 and 5 that can be accurately represented as there are between 90, and 95. Now we're going to step forward again to floating point. Here's a graph of floating point. Now, I did not graph every single floating point number because it would just look like a solid blue line going across there. So I graphed every 2 millionth number that could be accurately represented. So we started with 0, and then you skip the next 2 million numbers that can be accurately represented, and you plot that one and plot that one. Notice that the dots are much closer together the closer you get to 0, which means that they can be much more accurate for smaller numbers than they are for larger numbers. And this is great because if you're measuring the width of the sun in micrometers, it's probably okay if you're off by 10 or 20. It's really not going to make that much difference. However, if you're measuring the width of a human hair in micrometers, you have to be a lot more accurate. If you're off by 10 or 20, you're going to double or triple the size of that hair. And so the fact that they can represent numbers and be more accurate for smaller numbers than they are for large numbers is freaking awesome. So remember a while back, we talked about that special value for the exponent, those 11 bits? Well, we're going to talk about what makes them so special. When those 11 bits have the value of 2047, or in other words, when all the bits are set to 1, you have this, I don't know what this slide is for. We're going to ignore this equation altogether. And instead, we're going to say when the fractional bits equal 0, you have infinity. And because we still have the sign bit, we're going to use the sign bit, you can also represent negative infinity. However, when the fractional bits are not 0, that represents nan, or not a number. Now, if you want to play around with infinity in JavaScript, you can use the infinity keyword there. Or you can just do any positive number and divide it by 0, and that'll give you infinity. If you want to play around with nan, you can use nan. Or you can take a number and multiply it by a string, and that'll give you nan, because that is not a number. So floating point numbers are versatile. They can represent really big numbers, really small numbers, infinity, also negative infinity, even though it's not up on the slide, and nan. Now, there's a lot of discussion that we could have about why floating point numbers are represented this way. Why did they choose 11 bits? Why 52 bits? Why all these other things? But in the interest of time, we're not going to have that discussion today. But I hope that you have a good mental model of how they work. Floating point numbers are represented using an exponent. They can represent big numbers and small numbers. They can represent nan and infinity and negative infinity. And they are more accurate with smaller numbers and less accurate with larger numbers. And that's the end of floating point. There are a lot of other ways that you can represent numbers on computers. There's complex, rational, binary coded decimal, but integers and floating points are the most common. In the beginning, God created the earth in 7 days. And because there was only 7 days, he had to leave stuff out like this, and this, and this. But for reasons that I don't understand, there was enough time for this, and this, and this. In the beginning, Brendan Ike created JavaScript. And he did it in 10 days. And 10 days is longer than 7 days. In fact, it is 42.857% longer. But because Brendan is not as great as God, he also had to leave stuff out of JavaScript, like integers. But luckily, he had time to include floating point numbers. And you might be thinking to yourself, what? No integers? What about parseInt? Well, parseInt is a lie. It's a big, big, dirty lie. Note it's not a big, dirty lie. It's a big, big, dirty lie, and that's important. parseInt is really a lot more like parse float, and then you floor it, and then you still end up with a floating point number. So remember at the beginning talk, I was going to answer the question of why JavaScript treats 10 quadrillion as the same as 10 quadrillion and 1. Floating point numbers in JavaScript are less accurate as they get bigger. They can't represent all of the numbers as accurately as they can when they're smaller numbers, with smaller numbers. JavaScript can accurately represent the number 10 quadrillion. And it can accurately represent the number 10 quadrillion and 2. It cannot accurately represent the number 10 quadrillion and 1. And so it truncates it or rounds it down to 10 quadrillion. Now, and so that is why 10 quadrillion is equal to 10 quadrillion and 1 in JavaScript. And you may be asking, why down? Well, that's another homework assignment for you. If you want to study rounding modes and Google rounding modes, you will find the answer to it, and it's a lot of fun to study. So there's a couple gotchas that you need to deal with when dealing with floating point numbers. We've already talked about 10 quadrillion and 10 quadrillion 1. You want to be careful when doing math that involves, or addition or subtraction that involves big numbers, really, really big numbers, and really, really small numbers. If the small number is too small, it may not be enough to bump the big number to the next number it can actually represent, and you may end up with that original big number. For example, 10 quadrillion plus 1 gives you 10 quadrillion. You need to remember that nan is a thing, and you need to deal with that in your code. Also, infinity is a thing. It's usually a bad idea to compare numbers with equals equals or equals equals equals. Comparing them like that with floating point numbers is a bad idea. And the reason why is because of rounding, things that should be true or are true in math aren't true with floating point numbers. For example, 0.1 plus 0.2 does not equal 0.3. You can try it out at home if you'd like. So instead of doing this, you should instead Google how to compare floating point numbers, and then you should cry because it's really, really complicated. Now, NPM has a lot of libraries for doing that comparison, and a lot of them are buggy. Plus, your application is going to break when somebody unpublishes it in Rage. So this isn't perfect. It does a pretty good job of comparing floating point numbers. You may want to use something like this. It doesn't work with infinity, and it doesn't work with nan, and you may need to add code to handle those specially. So anyway, good luck with comparing floating point numbers. So that's the end of the gotchas. So I hope you remember today that even though floating point numbers can't represent 10 quadrillion and 1, and even though they have some gotchas, the floating point numbers are still frickin' awesome. And the end. I'm Evan Fair, and I still tweet occasionally at Evan Fair, and I still have way too many letters in my name. And that's it.